I think. Okay, so our next speaker is Ivan Sechin with the talk Quantum Rmatrix Identities and Interacting Integrable Tops.
Well, thank you. I will try to share my screen.
Allow me, sorry.
Okay, so we can see it.
Well, let's start. And do you hear me? Hope yes. And today I'm going to talk about quantum matrix identities and interacting integrable tops. And we have seen today several talks from Andrei Pogrebkov's colleagues. And now I would like to say that he is also an active participant of a mathematical life in Moscow, and he is a professor in Higher School of Economics and one of the organizers of a seminar in integrable systems in Steklov Mathematical Institute, where this work was done. Well, and let me start with the plan. And I would like to begin with introduction about classical integrability and functional relations which provide it. And after that, I would like to show how these identities can be generalized to a non-abelian case using quantum R matrices. And after that, I would like to say a few words about relativization, quantization of such integrable systems and some result about integrable system obtained via this generalization. Well, and I will start from a very classical point, classical integrability. And during this talk, we will consider only finite dimensional integrable systems with a finite dimension of the phase space. And so we can see concretely, we can say concretely what is an integrable system. We should have half of dimensional conserved quantities, which is independent and for some commuting. And the instrument to get it, it's first point, we get Lex pair, and the second point is a classical R-matrix structure. And Lex pair provides conserved quantities, and classical R-matrix structure provides Poisson commutativity. Well, and for example, there are many particle integrable systems in classical mechanics. For example, Calogero one, and we have such a Hamiltonian, and it can be generalized where interaction constant become different between different particles, and it is a spin Calogero. And we also know that there are three integrable cases: rational, trigonometric, and elliptic one. Well, and another example, another family of classical integrable system are integrable tops, for example, Euler top. And there are also three integrable cases with rational functions, trigonometric functions, and elliptic functions in their descriptions. Well, and Euler top can be generalized and all these systems are integrable, both many particle Calogero systems and top systems. Well, and why are they integrable? And the reason is the same for particle systems and top-like systems. For example, one can write a Lux operator for spin Calogero, or in the same way, one can write a Lux operator for top system. And in both cases, both particle one and top one, integrability follows from one relation on one function phi, called here, and it is a quadratic relation. You can see it in the center of the slide, and it holds true for all three cases: for rational one, for trigonometric, and for elliptic. And the same function and the same relation works both for particle systems and top systems. And it is a very classical theory. It is well known. Well, and let's switch to the generalization. And we begin from the classical functional relation for integrability of our classical systems. And now let's notice that quantum Rmatrix satisfies a very similar quadratic relation. One can just get this Young Rmatrix and check that we can, instead of phi's here, write Rmatrix, and this Rmatrix is a very large matrix in a large space in a tensor product, and it acts non-trivially in spaces 1 and 2 here. And these spaces are the same as parameters in our matrix. For example, here we have Q1 minus Q2, both and here, and spaces in which our matrix acts non-trivially is 1 and 2, and in all places the same. Well, and one can check it that it holds true for example, this simple matrix. Well, and naturally, we can call it a matrix non-abelian generalization of the relation on phi above this one. And here we can, for example, change the order of phi's, but here the order is fixed. Well, and as soon as we have such a functional relation on our matrix, the idea is, but no, let me first say about that this relation is not only for the Young matrix, but also for elliptic and trigonometric solutions. We can write XXZ and XYZ quantum matrices, and it also works. And moreover, why we call the solutions of such a quadratic relation quantum matrices? Because with two natural properties, the symmetry one, we can change the order of spaces with changing all parameters with opposite, and the unitary, which says that R12 and R21 are not opposite, inversed. And if we have any solution of this quadratic relation with these properties, it is actually a quantum matrix, which means that it solves Yang-Baxter equation, and it is a short calculation. But of course, not every solution of quantum matrix, not every solution of the ordinary Yang-Baxter equation solves this one. Because, for example, here we can multiply all r's on scalar function, but here there is no such freedom. We cannot multiply r's here on an arbitrary function because here are different r's in different summations. Well, and the idea is to get new integrable systems by replacing phi's with r, because we have quadratic functional relations on phi and on r. And the generalized systems, interacting integrable tops, can be obtained from the spin calogero one by replacing in a diagonal part. Here we had phi in spin calogero, but now we replace it with quantum matrix, and with some regularization here for compatibility. And here we can use any quantum matrix of any size, for example, not connected with number of particles, for example. We can use any R matrix, and for this L, we can construct a second operator in a pair, and also a classical R matrix for every L, for every quantum R, which satisfies the quadratic relation. And this relation, as in a ordinary scalar case, this relation provides a classical integrability of this generalized system. Well, so at this point we get for any solution of this quadratic relation on R, a classical integrable system. Classical integrable system constructed using a quantum matrix. Well, and I started today with two examples. First was many particle systems, and second one was top system. And it appears that this generalized system, in case M equals 1 size of quantum R matrix, becomes just spin calogero, because we don't have any more matrix, we have just a scalar function. And on the other hand, in N equals 1 case, we have only one particle without any motion. For example, if we fixed momenta, and only one matrix S, which actually determines Euler top, which can be written in the terms of our matrix 2. So we have a system which simultaneously generalize both many particle systems and top-like systems. Well, and we know also that there are, for example, not only calogero many particle systems, but there are relativistic generalization Rusinar's ones. And the same picture is for tops. And these generalized systems has also such a classification. We can also generalize a relativistic model. And we can add additional parameter eta And without this filter, we get generalized tops from the previous slide. For n equals 1, relativistic top. And for m equals 1, just ordinary Rusinars. Well, and we have also a generalization of particle and top systems. Well, and all slides before, I showed you only the lex operator. But now, let's switch to the second component of the classical integrability, classical Rmatrix structure. And these classical structures are different for top-like system and particle-like system. For integrable tops, we have non-dynamical classical Rmatrix structure. That means that these Ls, of course, contain spins, momenta of the top. But here, this L, this R doesn't contain S at all. It's just a number matrix without any dynamical variables. However, in a particle system, we have a different behavior. We have here we have both, for example, momenta and coordinates, and here we also have coordinates. It depends on additional dynamical variables. Well, and it leads to, for example, different classical Young-Baxter equation on these R matrices. And these are two different structures. But our generalized system actually generalize both these structures too. And we have both dynamical and non-dynamical appearance for classical matrix. It doesn't depend still on S coordinates, but depend on coordinates Q. Well, and there is also a quantum version. And in my talk, non-dynamical quantum matrices, which corresponds to tops and their quantizations, replaces 5 functions. And for example, 6 vertex or 8 vertex are matrices, which are just a numerical matrices. And in dynamical case, R matrices contains additional dynamical variables, and quantum Young-Baxter equation becomes more complicated with some dynamical variables and even shifts. And also we have 2 different quantum algebras. In non-dynamical case, we have Sklanian algebra in an elliptic case. And in dynamical case, we have a small elliptic quantum group introduced by Felder, Tarasov, and Varchenko. Well, and in our generalized case, we have also generalization of these 2 pictures. We have generalization, for example, for these 2 quantum R matrices. You have to write instead of these 2 phase R matrices of this type. And we have generalization of quantum dynamical Young-Baxter equation, which becomes partly dynamical, not on all variables, but in a part of them. And we have also a generalization of these two quantum algebras. We have a generalization of Scalanian algebra and small elliptic quantum group, which looks like we have m² copies of Scalanian algebras, which connected between each other by small quantum group relations. Well, and this is a short picture, something like a conclusion. What was happened? That we constructed generalized classical integrable systems using quantum matrices, satisfying additional quadratic relations, and we have top family of integrable systems and particle family of integrable systems. And these generalized systems generalize both the left-hand side and the right-hand side. And how it can be possibly applied for other integrable systems. For example, we know that quantum spin calogera system connected by freezing trick with long-range spin chains introduced by Haldane and Shasta. And for these chains, we know that they are integrable. They are connected with Yangian symmetry, and we can construct a lot of commuting Hamiltonians from the quantum determinant. But now we introduce a generalization, actually, of this spin calogera system, which is generalized interacting integrable TOFs in the trigonometric case. Well, and we hope it allows us to describe integrable anisotropic analogs of this Haldane-Shasta chain, because here we have only XXX chain, no anisotropy at all. But what about, for example, XXZ and XYZ? And it is a possible direction. Well, and I would like to conclude. I showed you the generalization of classical integrable systems constructed using quantum Rmatrix, and generalization of a lot of different structures in integrable systems using it. Well, and we hope that it will be helpful for description of some quantum systems too. Well, and this is the end of my talk, and I would like to congratulate Andrei Konstantinovich with his university, and thank you for attention.
Thank you very much. Please, questions.
Sorry, I have a simple question. What can you say if you consider continuous limit of your model? I don't know, some model, continuous. Say, let's consider, say, for instance, I don't know, ferromagnets.
If
What
we, I don't know if it works, but no, for example, for this chains, I hope it works. But I don't know for any dynamical.
But however, as we know that in a classical case, you have a Lax representation in such a case for Landau-Lifshitz equation. So for one-dimensional case, and the question is, what is it possible somehow to perform some generalization in quantum case, for instance?
Like calogera Landau-Lifshitz
Yes, yeah, something like that.
I hope yes, and it can be done, but I don't know if some which model is is a limit, but I hope it is probably can be generalized, just straightforward.
Okay, thanks.
Structure is the same, but some additional work because of non-abelian is necessary.
Sure, Razumov, you wanted to ask some question? Please, other questions, if any. Well, let's thank our speaker.